In this segment, what I shall be dwelling on is how are these three-phase diagrams constructed? How do we represent three different phases which I talked of in the last lecture on a two-dimensional one? Let me start off from here. Let us forget about these parts. This is a two-phase diagram of a system AB. This is the temperature scale. This is the temperature scale. Ignore this part for time being. So here, this is the melting point of A. This is where the melting point of B is. And the standard eutectic, which you know, this is over here. So in this two-phase diagram of A and B compound, which are necessarily oxides, we have this region, this is the eutectic point, this is the melting point of A. So all of this area will be a liquid. This will be liquid plus A. This will be liquid plus B. And then I'll have a mixture of A and B. When we construct three-phase diagrams, we actually construct it around an equilateral triangle. Now, because this is a freehand drawing, all of the axes may not appear equal. I'm a poor learner. So when we are constructing three-phase diagram, say let's say A and B, what we have on this is the AB axis. The temperature curve is on the vertical plane. So this vertical axis will represent the AB. This particular axis will represent the BC, and this will represent the AC. So when three-phase diagrams AB, BC and CA are held vertically, the temperature axis is always vertical. The composition axis is always on the horizontal. So this is the 100% A end of AB. This is the 100% B end of BC. This is the 100% of AB. This is the 100% AB of BC. This is the 100% C of BC. And this is the 100% C of AC, and this is it. So what we have over here is this eutectic line corresponding to AB. This eutectic line is corresponding to BC. This is for BC. This is for AB. And this one is for AC. So E1, E2 is the eutectic for AB. E3 is the eutectic for BC, and E1 is the eutectic for AC. Now, when I'm having each of these phases individually, that is, I am talking of AB phase over here, yes, the eutectic is E2. If I am talking of BC, the eutectic phase is E3. Similarly, E1 is the eutectic phase of AC. But when we have it, what happens? We have got three eutectics, E2, E3, E1. Necessarily in a system where I have got AOX, BOX and COX, I have not written the oxygens for simplicity. All these three eutectics, they will also form a final eutectic of its own. Here what happened? This is the liquidus line for this binary system. Each of these lines are the liquidus lines for the binary system. But during the during in three phases, each of these three binary eutectics will form their own eutectic, which occurs at a much lower temperature. So what we now have is, on a three-phase diagram, this plane. This is one eutectic plane. This is the second eutectic plane, while this one is the third. These three eutectics, E2, E1 and E3, they combine together to give us this final eutectic. So what we have on this three-phase diagram, this is two-phase and two-phase. I have combined it three-dimensionally. What we will have is this eutectic over here. This E3 would possibly correspond to a point E3 on the BC over here. This E2 would correspond to a point E2 over here on AB, while E1 would correspond to a point E1 on this binary AC. And we would have E1 of this binary eutectic represented here, E3 the binary eutectic of BC represented over here, and E2 the binary eutectic of this AB system represented over here. If I make this diagram a bit more complex, what I will land up with is this line is the projection of this line. This line will be the projection of this particular line, while this line would be the projection of this particular line. So essentially, by drawing this on this two-dimensional scale, what we are saying is these lines on the two-dimensional ABC are the projections of E to E, which is this, E1E, which is this, and E3E, which is fundamentally this. In a sense, we do not have to draw a complex diagram as this. What we would be doing is having a diagram which says this would be the projection of this entire thing on a two-dimensional diagram. And this is the way we start simplifying. So in this particular diagram, what we have done is we have brought, I am repeating again because this requires a concept of three dimensions, and you have to imagine a bit, three different phases, three different eutectics, binary eutectics, they melt together, react together, giving us on the two-dimensional diagram this sort of a joint. So these lines, I reiterate, this E1E line is a projection of the E1E line. This E3E line is a projection of this E3E line. And this E2E line is a projection of this E2E line. Now let me take this further. Now before I come to this, and from this diagram, what it means is this area is the primary phase of C. This area is primary phase of B, while this area is the primary phase of A. If you remember, if I don't think I have those diagrams. When I showed this particular diagram, I said 7 is MgO. Now you understand why did I draw this. In line with this, this is the primary field of MgO. In line with this is the primary field of silica. And in line with this is the primary field of alumina. So this is the reason why I had shown that particular diagram. Now let me take things a bit further over here. I have already drawn the lines E2E, E3E, E1E. Now let me bring in the temperature axis. You see, the vertical lines axis are the temperature axis. This particular surface, which is over here, I have been drawing repetitively. This particular surface, these lines had a meaning which I did not explain still now. This is where I go to tell you why did I draw these lines. You see, over here at this temperature, this T1 would cut this liquidus line over here. That is the liquidus of A3C. The same temperature line would cut the liquidus of E1C over here. And the whole surface is curved. As a result, this represents the isothermal line for T1. Similarly, this curved line represents the isothermal line for T2. Each of these curved lines, or if I come back over here, each of these isothermal lines represent the isothermal lines due to the temperature on this particular axis. They all represent the isothermal lines. Similarly, these are all isothermal lines. Having said that, let me now project these isothermal lines on the two-dimensional one. Let me say what I would end up with and then come back and say why. If I project these curvilinear isothermal lines on a two-dimensional one, I would get lines like this. All these T1, these lines are isothermal lines, which have been shown over here. And so, what we have is basically here the primary phase field of C, which is bounded by this line E1, E3, primary phase field of B, which is bounded by E2, E3, and the primary phase field of A, which is bounded by E1, E2. I will come back to this diagram again to make another point later. So, in line with what I showed in this particular one, what has been done over here is these isothermal lines have been projected on this particular A, C, B two-dimensional paper. This A, C, B is the two-dimensional representation of the entire three-dimension which is over here, because this is how it is done as I had shown you earlier. Now, why did I say it? First of all, if I come back to this diagram, you have to appreciate one thing. E1 is at a temperature which is lower than the melting point of A and lower than the melting point of C. So, E1 is the eutectic point of the system AC. This E is the eutectic of E1, E2, E3, and so the temperature is lower. So, I can say that this is the direction of falling temperatures. This line represents the direction of falling temperatures as I go from E1 to E. Similarly, this joint E3 to E again represents the direction of falling temperatures from E3 to E. Or as I say, if I have a pure AB system, BC system, I am increasing the amount of A added more and more, the eutectic temperature shall follow this particular line to give me the three-phase system. Similarly, E2E, again this line represents the direction of falling temperatures. So, the melting point of E is lower than E1, E2, E3, something which was very obvious when this graph was shown. I had stated that the TE temperature of this eutectic is much lesser than this, and hence these joints E1E, E2E and E3E give us the direction of falling temperatures. Now, this has relevance which I shall go on to explain, possibly not today, but maybe the next day. Let me come back to these graphs. So, I have already said that the direction of falling temperature is this. I don't want to clutter this graph up. E2E is the direction of falling, E3 is the direction of falling, and the E1E is the direction of falling. Now, let us take a composition which corresponds to X. In the three-phase part, when I am having a three-phase 3D diagram, what will happen? Or even in the 2D diagram, what happens is I have got a two-phase system, AB, this is the eutectic, I take a composition here, this is all liquid. As the temperature falls, this is the temperature scale, excuse me, this is where the first solid starts forming. Then as I keep on coming down here, more solid forms, more B forms as I keep on going down, and here it is all A plus B. Similarly, over here in the if I am drawing on the three-dimensional system in a 3D plane, what will I see? If the temperature is over here, the whole thing will be molten. As I cool down, decrease the temperature, everything would stay molten until I have reached this point 3. This is where it first intersects this particular plane. And as a result, this is where the first solidus will be formed. I keep going down. At the next temperature at T4, it is intersecting over here. 5, 6, 7. So what happens is, as I keep going down, this T4 is being intersected at this particular temperature on this point of the graph. So it will follow 3, 4 dashed, 5 dashed, 6 dashed. By then, it has started encountering this eutectic line. So then it follows along 7 to E. So if I plot the cooling path, what would I see? I would see that the first solid phase start precipitating at 3. As I cool down, more solid phase precipitates at 4. More solid phase precipitates at 5. At 6 dash, the first eutectic composition separates out. Then the cooling will occur along the E1E eutectic line. So far it has occurred on the two-dimensional plane on this way, that is the join of C with all these temperatures. As it has reached 6, which is at the eutectic line over here, what happens? It encounters the E1 eutectic line, and then the cooling starts in this particular path, so that all materials freeze at this particular point, which is the E. However, if the composition was here, let us say I put it over here, and let me say label this 1. Obviously, what would have happened? This would have started off from here. It would have followed the same procedure, same path, this join C6 dash. But then the first crystals would start coming out here, which would go down to this eutectic line and finally forming at eutectic over here. So here what we get essentially are, if I start off from that, the cooling path of any composition X. It can be here or here. For example, there is a Y over here. I have deliberately drawn it. Obviously, you can see this Y is hitting this A1E. So what happens with the Y is the cooling path will then be following in this particular way. It would come here and then it would come straight over here. It would not follow this because there is no intersection. Here you have to remember this cooling path intersects the E1E line. Here for this Y, the cooling path does not intersect the E2E line. So Y would directly come down here without any other routes. Now, what I would like to do is be a little more, I would say, of an explorer by trying to find out if you understand the three-phase diagram. So what I am going to look at now is not this. Let us assume that we have a composition which corresponds to this. In that case, if I take this particular diagram, how would, now you got a two-phase diagram because I am now reducing everything to this. How would it look like? Well, it's difficult to show this both on the same plot. Let me try my best. What I'm trying to show on my left is basically this section SC, and I have reduced it to a two-phase diagram. Here you see I have stated I am going to intersect 4, 5, 6 dash. Here it is coming down to this. X intersects it at T3, comes through 4 dashed, more C is formed, the amount of liquid decreases, and it reaches T6, which is over here. If you now notice the difference between this diagram and what I had over here is this eutectic is no longer in this phase field. It is out of it. So what you do not see is this cooling part. T6 is the lowest melting eutectic in the cis section SC because this is out of it. You have to mentally visualize how is SC different from what I've been saying so long. I have merely taken a vertical section SC which leaves out this TE, and as a result you do not see this eutectic over here. That is, you do not see this join anymore. Rather, here is the lowest melting over here. I'll come to where how TE comes up again. At this particular end, S, what do I have? I have this melting one. And here A forms and just cools down to 6 dash. This 6 dash, then in this section C, now I am bringing in this whole section, is this forms that UTE, the final eutectic, where I have got both A plus B separating out, A plus C separating out, and finally below the ternary eutectic I have got A plus B plus C. This vertical section is very important at times because we have to apply the lever rule to determine what is the relative amount of solid and the liquid phases. In order to determine what are the phase compositions, how a situation cools, let me take the most simple example. Here I have got a system ABC with 3 binary eutectics which finally form a ternary eutectic. And I have got a point composition corresponding to Y. What I have to determine here is when I take a mixture, solid mixture, which corresponds to the composition Y, which I again to reaffirm say how will I measure it? I will drop a perpendicular on these 3 axes. So this length, let us say C, this is B, this is A. So C by A plus B plus C multiplied by 100% gives is percentage of C. Similarly, B by A plus B plus C multiplied by 100% is percentage of B, and similarly A divided by A plus B plus C multiplied by 100% is percentage A. So I have taken a solid which has got this much amount of C, this much amount of B, and this much amount of A. I have melted it and I am cooling down. Now how do I construct the cooling curve? At the very outset, what I would do is this Y is in this phase field. So I'll start off from A and then draw a straight line through Y which would intersect the eutectic line E3E over at this point. Hence, up to this stage, at the temperatures represented over this, nothing would happen, it would cool down. But right from here, as it is coming down, phases will start precipitating. If I draw this line, it would cool along this line, cool along this line to this until the temperature reaches of that of this eutectic. Now, this particular point, Y, by the method I had shown, has got 16% C, 25% B, and 59% A. So here I have drawn the line A through Y to this eutectic line E3E. These blue lines T1, T2, 3T, T4, T5, T6 are the isothermal lines. We see what I have chosen is where does this tie line intersect, say T5. I have chosen, say, this particular point 5. This is where it intersects. At the next time, just like in two-phase diagrams, the next isothermal line I have chosen is T6. This is where it intersects. Let us talk of what happens at 5 dash. At 5 dashed, what is going to happen? As I said, there will be melt and solid starting to separate out. Let us do two calculations. First, at 5 dashed, amount of melt, and that is this distance AY, because this is a melt, I am applying the lever rule, divided by this whole distance A5 dash. And the amount of melt comes out to be 86%. At 5 dashed, what is separating out? A, because it is the primary phase field of A. So during this cooling, A is precipitating out. So what is the amount of A? What is the amount of crystals of A? And that is given by this distance Y5 dashed, which I have given over here, divided by A5 dashed multiplied by 100%, which gives the amount of crystals that has formed is 14%. So as this sample Y is cooling at T5, I have got 14% A crystals separating out and 86% of the mass is still a liquid. Now obviously, again, if you drop perpendiculars from here, you can find out what is the composition. I leave that to you to find out the composition of liquid. Obviously, as A is separating out, the liquid gets richer in B and C. As cooling proceeds, what will happen? I have chosen the next isothermal line T6. At T6, what do I expect? Again the same way, this is the AY is proportional to the lever rule amount of liquid, now divided by this entire A6 dash, multiplied by the 100, and that is the percentage of melt, and it comes out to be 70% of the mass is melt. While Y6 dash divided by this entire line A6 dash multiplied by the 100% gives you the percent of the crystals of A. So you see here, what am I seeing? As it is cooled from 5 dash to 6 dash, more and more crystals, that is 15% from 14% crystals of A at 5 dash, I've got 30% of crystals at 6 dash. Of course, you can again calculate the composition of the liquid by dropping perpendiculars from here, calculating, and you will find that the liquid is getting richer and richer in B and C. Now let me take the point 7 dash. Here the line has intersected the eutectic joint E3 and E. It means now what will precipitate? Both A and B, because this separates the primary field of B from A. So as I had said, cooling, let me take a clear graph. As I had said, once it reaches this particular point, cooling would go on in this particular format. So as I go from 6 dash to 7 dash, I am moving to a phase where I have now at 7 dash, when the joint AY has been extrapolated and it intersects the E3E, I have got both solid and both the solid phases A and B separating out along with the liquid now getting richer in C. Let us see what happens at 7 dash. At 7 dash, what I have done is I have, okay, let me explain a bit. This is the E3 line. I have deliberately stopped the AY line over here, a very small fraction away from touching this, in order to say, hey, what is the composition separating out just before it touches the E3E? And what it turns out, again, using the same principle as outlined earlier, is AY divided by the entire length multiplied by the 100%. That is, over here, if I am looking at the melt, it is AY divided by the entire length multiplied by 100% gives the weight percent of the melt. You can see that the amount of melt has decreased. Crystals of A, as I have stopped just short of touching this line. Crystals of A at 7, as I have just stopped short of touching this line. About 45% of the solids will separate out as A. As I have said, the cooling will proceed along this. So let us see what happens at 8 dash. Again at 8 dash, applying the same familiar river rule, there is AY. Now for 8 dash, I have got problem. 8 dash is over here. So for drawing the entire line, what we do is, because it is the two phase, we take that particular point and I have drawn this line through Y. You will see 8 double dash is the extrapolation of the line 8 dash Y onto this axis AB. Why? Because at 8 dash, it is no longer pure A. It is both A and B phase fields which are separating. So I cannot draw through 8 dash from A. What I have drawn is, at this particular point, I have drawn a joint 8 dash Y to this particular point 8 double dash, which is an extrapolation of the axis AB. At that particular point, now the lever rule changes a bit, because now 8 double dash Y will be the amount of the liquid, whereas the total length is 8 double dash 8 dash. So here I have, over here, I have got 45% of the melt, mass as melt. And what is the amount of solid? Obviously it's 55%, which can also be reduced by 8 dash Y divided by this entire length 8 double dash 8 dash. This solid, as I had said, will be consisting of both A and B. How can I determine? what is the amount of A and B separating out. What I have done over here is now to determine the relative amounts of A and B which are separating out at this point A dash, which is at the on the eutectic joint E3E, which separates the phase field A and B. I have now got to use a different set, that is over here I will use this particular axis. It's wrong thing I had done. This whole length 8 double dash 8 dash is this whole length, and over here if I draw this 8 double dash A and 8 double dash B. 8 double dash A is proportional to the amount of B because they are opposite. Lever rule says they are opposite. So this length is proportional to the amount B, while this length is proportional to the amount A. And this is what I have done. 8 double dash A divided by this entire length AB gives me 16% B, and 8 double dash B divided by AB multiplied by 100% gives me 84% A. So at 8 double dash I have the situation where the melt is there, A and B are separating out, and by using the lever rule I can measure what is the percentage of B and what is the percentage of A. Near the eutectic point, as we come close, you are familiar with what you do in two-phase diagram. Near this TE, temperature of eutectic, what are we faced with? Here what has been done is, again I have assumed near the eutectic point over here, I have extrapolated this joint 9 dash, too much crowded, 9 dash through Y to 9 double dash. So if I am combining both the graphs, let me see. Yeah, if I am combining both the graphs, then 9 double dash Y divided by this whole length 9 double dash E corresponds to the melt, which is this, which is 40% melt. Whereas YE divided by 9 double dash E multiplied by 100% gives the amount of the solid, which is given over here. This percentage of the melt you can determine by dropping perpendiculars. Again, following the same principle, that is, I can determine of this 60% solid, how much is B and how much is A. How? Just as a repeat of the last temperature, 9 double dash A divided by AB will give you the percentage of B, which is 22%. While 9 double dash B divided by AB will give you the amount of A. Now, so essentially, as we are in this particular three-phase diagram, to repeat before I move on, I have taken a material of this composition, Y, and what has happened is that it has got a composition of C and 16%, B 25%, and A 59%. When the temperature has reached this isothermal line T5, it has started cooling. Crystals of A separate out. I cool more A separates out. At this, when it encounters this E3 line, join of the eutectic, A and B start separating out. As it moves towards E, more A and B separate out. And finally at E, A, B, and C separate out at this ternary eutectic. Now, this is the simplest example of how these systems work. Let me move on to more complex systems. This is a system where I have got, I'm starting off with a material which has got certain amount of A, B, and C. This is ABC. And there's a binary congruently melting compound also formed. Here we have 4 eutectics, because this triangle, this joint CAB, separates this part from this part. So essentially what we will have is 2 ternary eutectics, E1 and E2. The arrows which are shown are the directions of the falling temperatures. These are the isothermal lines. All of these are isothermal lines, and the arrows indicate direction of falling temperature. Obviously, what I have not drawn over here, this is also the direction of falling temperature. This is the direction of falling temperature. This is the direction of falling temperature. This is the direction of falling temperature, and this is the direction of falling temperature. So essentially it means that if I have a composition which say corresponds to this particular point, it is in the primary phase field of A, C, and AB, and it will finally crystallize in this eutectic E1. So if I have got this triangle with this binary join, and if I have got a point over here, the way I would draw a cooling curve is by drawing this line and then following it up to the eutectic. If I have a point over here, it is the primary phase field of A. I would draw a line through here and then follow it through the eutectic, making the compositional calculations as I had done earlier. For these 2 points which I have done, if I am taking this point, what will happen? A will separate out. It will keep on separating until it reaches this E1, E2 join. From there, A and AB will separate out. As I progress more and more and more to this E1, I will have A, C, and AB separating out. While if I have got a point in this half of the triangle, because this joint separates the whole triangle, in that case I would have drawn a line starting from AB through this particular composition with which I started, which would intersect this eutectic joint E3, E2. And hence, as it cools through here, what would have happened is more and more AB would have separated out as the cooling progresses from here through here. At this point, AB and B will separate out. At this point, AB plus B will separate out. Cooling will progress till it E2, A, B plus B plus C separates out. This is one of the situations which you may face in these ternary compounds. We may have a congruently melting binary compound, and in that case the way to determine the cooling curve is by making the join, drawing the lines up as I had said appropriately. Let me say what would happen if I had a composition over here. I would have to, this is the primary phase field of C. So I would draw a line through C, from C through this particular point. It would cool down to this particular thing and then finally cool off at the eutectic. There are many other situations which are possible. This is a major problem. I would simply cut it briefly. This is an incongruently melting ternary. Look what has happened. There is a peritectic point, and this peritectic point is outside this. What could have happened is, an alternative is the peritectic could have been here, that is over here. Well, there are various possibilities, but let us ignore this red line for the time being. First of all, this peritectic point falls outside this triangle BCAB. This joint does not intersect the peritectic as I have shown this way. So what will happen? Suppose I have got a composition corresponding to here, or rather I have already got a blue line. The way it would cool is, it would cool along this path, go to this, follow this E1 EP line, and then everything freezes at the peritectic. However, during this point what is happening? B is separating, A is separating, and at the peritectic AB plus C will separate. However, if it is from this particular point, the cooling path would be something like this over here. Let me say a particular point over here, this particular point. The cooling path now would lead to a different situation. It is cooling over here. At this particular point, the phase field which is separating out is BC. As it hits this line PE, A and BC separate. At this particular point, A plus BC will separate. Finally, at the eutectic point, I will have A plus BC plus C separating out. You see, there can be lots of variations to these three-phase diagrams. These three-phase diagrams come in very important when we are talking of liquid phase sintering. This is not so important in solid phase sintering, but the very fact that we have a range of operations like the silicon nitride which are best sintered through liquid phase sintering, many of these diagrams become operational. But however, let me say, most of the diagrams are not this clean cut type. I had earlier shown you, when I had introduced three-phase diagram, how complex it can be. There are so many different phases which are separating. So it requires a thorough understanding of these cooling curves, how to cool, which is really not within the ambit of this particular course. In fact, it is a course by itself, or half a course. For the time being, what I would want to end you with is, there can be systems and systems and systems. A very simple system over here, a little more complex system, and finally here is a lot more complex system. This is a binary incongruently melting system with a peritectic, and there is no end to it. One has to carefully read how to go through it to have a proper understanding of the whole thing.